Hi Math 213. In this video we're going to be beginning our work with geometry and starting with section 11.1. We'll only be getting into the beginning part of section 11.1, discussing some of these basic features of geometry, and then we'll be continuing to discuss section 11.1 when we come back to class this coming week. So the first thing I'd like to do is at least get you to think about how we need to be thinking about geometry as future teachers and what some of these standards look like for geometry. So for grades pre-K through 2, students should be able to recognize, name, build, draw, compare, and sort 2- and 3-dimensional shapes. They should be able to describe attributes and parts of 2- and 3-dimensional shapes. Investigate and predict the results of putting together and taking apart 2- and 3-dimensional shapes. For grades 3-5, the standards look something like this: sort, build, draw, model, trace, measure, and construct the capacity to visualize geometric relationships. Learn to reason and to make, test, and justify conjectures. And for 6 to 8, students should precisely describe, classify, and understand relationships among types of 2- and 3-dimensional objects using their defining properties. They also talk about using visual tools such as networks to represent and solve problems. This is just a technique that is discussed in the standards. You'll discover what networks are later on when you're working in your standards. So some of the basic notions we're going to be working through are linear notions and planar notions, and discussing things in linear sense and in planes. We'll get into this other material when we're back together in class on Tuesday. So the fundamental building blocks of geometry are points, lines, and planes. And what's unfortunate is that these building blocks are what are called undefined terms. What that means is that it's not possible for us to give a definition for what a point is, or what a line is, or what a plane is without invoking some other definition of geometry. Like a definition for a point would have to make use of what a line is, or a plane is, or some other feature of geometry. And likewise, the definition for a line would have to make use of what a point is. So it's kind of this circular issue where definitions for one rely on the other, but it kind of goes back and forth in this circular way. And a nice example of this kind of circular defining property or circular defining issue is in your book with the cute cartoon here by BC, and it doesn't use mathematics, but it uses a word definition. So here, this little caveman guy is looking at the word obedient in the dictionary, and it says to comply rather than resist, and it says see rebellious, and so he flips to it, and it says rebellious, to resist rather than comply, and it says to see obedient, and he goes back and forth and back and forth, and he just gets very, very frustrated because this is sort of defining words based on another word that uses it to define itself. So this sort of circular logic that we're seeing here to define these phrases here, or these words here, is troublesome. And this is a real hang up with geometry, is that to get at the very beginning of geometry, you have to just accept that there are what are called undefined terms here. We all understand intuitively what we mean by a point and a line and a plane, but we can't actually put a hard and fast definition for them because those definitions rely on defining these other things based on themselves, so it's kind of this circular issue. But we can just intuitively understand what we mean by a point. So for example, here we can say A and B are both points. C is a point. Yes, these are illustrative definitions in terms of, instead of verbal definitions, these are illustrative definitions. And here we can see L is a line, right? This is a line, or it's, for example, center line of a road. This is also a line. Now we're able to define a line based upon points, but again, we're going to do that in a second, but just understand that I could say this is a line. It is the unique geometrical thing that passes through these 2 points. We'll do that in a second, but understand that again, that definition for a line will depend upon using what a point is. Lastly, our building block of a plane can be seen here. An example is a tabletop. So a tabletop is a plane, or a wall, or a floor, or a window, or any of those things would be considered planes. And again, we'll be able to do a definition of what a plane is based upon using points or a line specifically. Okay, so these are illustrative definitions and examples of points, lines, and planes. So let's do a little bit more work with defining, trying to just come up with what exactly a line, a plane is. So a line has no thickness and it extends forever in 2 directions. And specifically, if we're given 2 points, there is one and only one line that connects these 2 points. Again, notice that to define a line here in this idea, we're using the idea of what a point is, right? without actually defining it, okay? Because again, that would require talking about lines, but that's circular. Okay. So an official sort of idea here is that if we have 2 points P and Q, we can create a number line on P and Q, on the line PQ, so that there's a one-to-one correspondence between the points on the line and the real numbers. And so what this really means, let me get my pointer here, is that if we had 2 points, let's say P is right here, and let's say Q is right here, I can create this number line here if I use the line PQ. This is the line PQ, right? It's the line passing through the points PQ. So I could actually say that there would be, I could put a number line in here so that there would be a one-to-one correspondence between the points on the line and the real numbers. So wherever you decide to locate 0, you could put it over here. It doesn't really matter. But once I do that, there's now a one-to-one correspondence between any point on the line and the real number. So for example, this point P here, that would coordinate with a number on the real number line. Again, it would depend on where you put the 1. Remember, we talked about this with the number line, that the unit is an issue. We can't really label any point and give it a value until we know where 1 is. For example, if I put 1 here, that makes a difference versus if I put 1 over here, right? So again, those kinds of issues would be precursors to being able to say what P and Q are would be specifically. Okay, so let's talk about some of these points now that we have the idea of a line sort of in our minds here. And get ourselves some vocabulary. So collinear points. Let's talk about what collinear points are. So collinear points are points that are going to be contained on the same line. So let's say this is line L here. Usually we denote lines with these lowercase scripty letters. Line L contains the points A, B, and C. So we would say points A, B, and C, they belong to point L. They are considered to be collinear, right? Collinear, right? Collinear, meaning they are contained on the same line. Points A, B, and D are not collinear or non-collinear because D is not contained on the same line as A and B. Likewise, B, C, and D would be considered to be not collinear. Okay, D is a point not on the line L is really what that means. Okay, so collinear points. This word between here, how do we say a point is between two other points? So point B is between points A and C on the line. This is an intuitive thing for us, right? Yes, we can kind of agree that this is true. And we could say point D is not between points A and C. Between really relies upon the point being considered being to be between being on the same line as the other 2 points, right? And a more specific way to write this, is to make use of this idea of talking about lengths here, right? So we could say, for example, AB right here represents that length here. And if I draw a little line here, right, AB would represent the length connecting A and B. To say that B is between A and C just means that if you take length AB, you can add that to length BC right here, right? So you could take this length and you could take this length, and that will equal the length AC, right? This whole thing. That's really what it means for point B to be between A and C, is that these 2 little segments here, when added together, equal the entire segment there, AC. Okay, and we'll talk about the word segment more in just a second. I know I can use that word because you know what it means already, but I'll define it for you in just a moment. Okay. So let's talk about line segments. Perfect intro into that, right? So segment into that. Here we have a line segment, right? A line segment is just a subset of a line that contains 2 points of the line and all points between those 2 points. So the idea is that we have a line segment AB here, and if we continued the line, right? Here, if we were continuing this line here, A is a point on a line L, you could call it line L if you want, B is a point on line L, and the line segment AB, written here like I just used that notation a second ago, is the line segment starting at A, or I guess being terminated at A and B here, and it consists of all the points between. Notice we had to define that word a second ago, between, so that this makes sense, right? So for example, this point is on the line segment AB because it is a point between A and B, right? And the line segment consists of all of the points between A and B, right? Okay. Also, sort of something that's you may have seen before in some of your other math classes is this idea of a closed segment or an open segment. So this segment that we have drawn here, this is an example of what's called a closed segment, where it actually includes the endpoints. It includes A and it includes B, right? So this includes the points A and B, right? We could have what's called an open segment, And that is a line segment where you don't include the points A and B, and you would write it like this with these little open circles on the end like that, right? And you would still label it as A and B. Right, so that's called an open segment, or you might have what's called a half open, or sometimes called half closed segment, right? Half open or closed. So half open, or you could say half closed, right? Either one of those words or phrases would be fine. And what this really means is that you have one endpoint included, one point included, and the other not, right? Say or. Here we can have this one open and this one closed. Right, so these are open segments, not including A and B, half open or half closed, and closed segments. Okay, so these are just some vocabulary, again, getting us sort of ready to continue working with geometry a little further. Let's talk about what a ray is. So a ray is a subset of the line AB. Again, imagine that there's this entire line AB, right? Okay, line L here, okay? So we have this huge line. An array is going to be a subset or a part of that line that contains the endpoint A, has A, and it has B, and all the points in between. So all this stuff here, it has the little line segment, but it has more. And it has all points C on the line such that B is between A and C. Okay, so what does that mean? That means B has to be a point between A and something else. Well, the only place that means is that C has to be out here somewhere, right? Okay, so it has to consist of all of the points A and B, but also all the other points C, so that B is between A and C, which means all those points headed out this direction, right? Okay, so we get this sort of headed in one direction kind of idea. And the notation here is written as this, right? A, B with a little arrow on the top. And this is actually directional, right? So you always write it sort of with, the beginning part of the ray written next to the letter that it starts at. So for example, if our ray went like this instead, oops, we'll start it here, and let's say it went this way and it went like this. Right? We would write this and denote it as this. Okay, because we want to say the ray starts at point B and continues in the direction of A. Right? So we would write it like that instead. So the way you write this with the little direction of the arrow actually does make a difference. Okay, so let's talk about some words in terms of a plane. What might be good first, and I don't know why they left this out of the slide, but we should talk about what a plane is. So a plane has no thickness and it extends indefinitely. Okay, so we're going from thinking about something that is a line, right? It's just a line continuing indefinitely in two directions to now a plane, right? So we're going from something that was two-dimensional, a line, right? A line is two dimensions. It extends indefinitely in two directions. And now we're thinking about a plane, right? So a plane is going to be sort of going like a piece of paper or wall or something like that, right? It's going to be going in lots of directions now. So a plane has no thickness and it extends indefinitely. And more specifically, a plane is uniquely determined by three non-collinear points, right? And if you need to repeat that, remember you can back up in the video. So a plane is uniquely determined by three non-collinear points. So that means you choose three non-collinear points, you can make a plane out of those 3 points. And so in other words, if we have three different non-collinear points, there is only one plane containing those points. So for example here, if we have points D, E, and G, we're able to make a plane containing those 3 points here, and that's this brown thing here. This is not supposed to be a trapezoid. This is supposed to look three-dimensional to us, right? And being able to see this as being three-dimensional, it's kind of a piece of paper that's fallen away from us a little bit, slanted away from us, right? This is containing the points D, E, and G there, right? Okay. And so we say that points D, E, and G are coplanar. Coplanar. They live in the same plane, right? So they are in the same plane. Okay. We can also say then that D, E, F, and G are not coplanar. So D, E, F. See this thing up here? F and G. F does not live in the same plane as D, E, and G, right? F is a point living above the plane, and it's sort of living above that piece of paper that is there. We can say that some lines are coplanar. So DE is a line living in the plane. DF is a line, where is DF? DF is actually this here. DF is the line coming up out of this plane, and FE are coplanar, right? So here DE is this line here, DF is this line here, and D and EF, I'm sorry, FE here, those are coplanar. So those would be a plane that is not shown actually on this illustration. It would be sort of a vertical plane, facing us, sort of living vertically in that sense. But those lines are coplanar. You could also say more specifically that there are lines on the brown plane that are coplanar. Let me erase some of these things. That cleans it up a little bit better. Yes, thank you. Okay, so what are some lines on the brown plane that we could say are coplanar? We could say DE and GE are coplanar. Yes, they live in the same plane. They're on the brown one. DG, DE, and GE are all coplanar, right? So they all live on the brown one. Yes, there are more planes that are shown here that are not shown here that we could actually talk about, and that's what these three are talking about, is another plane that's not shown. So let's see, DE and EG, that's the one I just said. Those are coplanar. Yes, and also DG, that would be the same plane as well. Okay, lines DE and EG are intersecting lines. They intersect at a point. They intersect at point E, right? Okay, so now we can start talking about lines and comparing them to each other. So for example, lines GF and DE. So GF is where? GF is this line coming up here out of the plane, and DE, that's this one living in this plane, they are what are called skew lines. They do not intersect. Notice that the line DE and GF do not intersect, yes? And they do not have a plane that contains them. Yeah, so if you think about it, you wouldn't be able to have this line GF living in the same plane as this line DE, right? And since they also don't intersect, we call them skew lines. Concurrent lines, lines DE, EG, and EF. Let me erase some of these little highlighted areas. Ooh, let's try that. Ooh, how about the felt tip pen? Let's try the felt tip pen. Lines DE, so let's see, line DE, ooh, that's nice. EG, that's this guy. Those are coplanar, yes, they live in the brown plane. And EF, let's see, that's this vertical line right here. That sort of cuts down through the plane. That little dashed line right there simply means it goes through the plane, and you wouldn't be able to see this little section right here that I just drew over. Let me show it to you a second. So right here, this little dashed line right here, this just means that this line EF would go through the paper and you wouldn't be able to see this section. You would really just see this part coming out down below. This part would be hidden from us. It would be invisible. Okay, but what they're trying to tell us is here that we have these two coplanar lines, and then we have this line EF, and these are concurrent lines. Not only are they intersecting lines in terms of pairs, but the three lines actually intersect, and they intersect at point E. So when three lines intersect, we call them concurrent lines. Okay, two lines intersecting is just intersecting lines, but three lines intersecting is a special word. That's concurrent lines. Lastly, we're going to talk about parallel lines. So we say two lines are parallel if they have no points in common, and this is the official definition for geometry of parallel lines. I know you may have heard of other ways to characterize parallel lines, maybe with slopes or something like that when you're working in the XY axes, but here we're not working in any axes. We have to just rely on our geometric notions, right, our geometric ideas. Okay, so if two points do not have any, if two lines do not have any points in common, they are considered parallel. And again, you can use this idea of they don't intersect, because if they intersected, they would have a point in common, right? So you could also say two lines are parallel if they do not intersect. That would be an equivalent definition. Okay, so for right now, we're going to stop our video on 11.1 there. What I would like you to do for class on Tuesday is take a look at table 11.4. 11-4, I should say, which is on page 636 to 637 in your textbook. I'd like you to take a look at that to prepare for class for Tuesday, and then when we come back, we'll discuss that together, and then we'll also finish section 11.1.